give the one or two liner definition. Then I give machine learns by itself,
Correct.
and that is a part of AI. So time being, forget about the AI because just I know machine learning. So come on the first statement, machine learns by itself.
Correct.
So taking the example that is very familiar, Boston housing price, basically, we have given some attributes, 506 which we have been provided. Based on that, we have to predict.
Okay. Correct. Correct.
So this is one-time algorithm I have given. Based on that, I am getting some prediction.
Correct.
But if this year info I can give again, assuming that is 100 row again, then it will be 606 lines, and machine will predict better. Is this correct?
Correct. Correct. So more the information you give to the model, the more better it will predict.
Okay.
Okay. So machine
And
learning, learning by itself, as in you have told a statistical model, and the machine, depending on the data, it is learning itself, right? I'm not forcing him to understand. See, if your crime rate is this, please do this. Are you feeding in if else statement? How do you do in traditional programming? If this
no,
password is matching, then go to this. If else, if this. So this is hard coding. You're telling the machine what to do. But in this, you have not told the machine what to do, right? You have not told that if my age is greater than 40, then predict, a heart attack. Age less than 40, do not. Have you told this? No. But the machine has, you have just given a model. Machine in itself is trying to understand how to predict that. Okay.
got it. Means more and more data you will be giving, more and more better machine prediction will be.
Correct. Correct.
Register learning itself. Got it. Thank you.
Okay. No problem. Okay. Just to give everyone a brief, a brief heads up on what. So I bought a device so that I can write on it, and so that you guys can see it properly. So um, sometimes, so there's a Shibudi user, so that I have logged in through my iPad. So in the meantime, whenever I need to write something, I'll give the control to that guy. I mean, to myself only, but to Shibudi, and you'll see the iPad screen, and then I'll write on it. Okay. So just to give you a heads up on how, so that I found it that I should have something to write on so that it's better to understand, everything. Okay. So let me share my screen. Okay, and I'll mute you guys. Okay. So okay, let's say I think I should start with the writing part only, so that it's better for you guys to understand. I'll just open the screen, and okay, just give me some 2 minutes. I think it has got disconnected. So just give me 2 minutes. Okay, guys, can you see my screen now? Okay. Okay, so are we fine? Everything clear? You can see my iPad screen and you can see and you can hear my voice, right? Thank you so much, Sunny. Okay, so let's start. So basically what we were doing is that we were discussing about decision trees, and so I told you guys that there are two approaches. One is the parametric approach, okay, so wherein we have a, type of functions where we have a particular structure of the equation, okay. Now this is called parametric approach. The other one is the non-parametric approach, wherein we do not have any equation, but I'll just change the color, but we have a process, okay. Now what is the decision tree process? So I think today I can write it better. So yesterday I told you you have to be very, you have to get this thing into your head that we are basically, whenever we are doing machine learning, we are basically dealing with a regression problem or a classification, okay. Now if you see, you can see my screen, guys. Okay, so uh, so basically a regression problem or a classification problem. Now regression is predict a continuous variable, continuous number. Classification is predict a class, okay. Now when you understand this, then it comes, the second step comes is which model to fit, okay. Now which model to fit is the decision that you have to take after you know that whether you have to predict a continuous number or you have to predict a class. Now regression has certain models that you can do. I started with linear regression, okay. Then we went on to lasso, then we went on to ridge, then we, I just gave a brief introduction of elastic net, okay. No need to understand this, I'm just giving an example. So basically in all these models what we are trying to do is we are predicting a continuous variable, okay. We also saw that knn can be used for regression. Now when we try to do for classification, how many models we have learned till now? We have just seen KNN and we have just seen logistic regression. Now, can linear regression be used for predicting a class? No. If I want a linear regression to predict a class, or I want a linear model to predict a class, then I have to go on to logistic regression. Okay. So logistic regression we have seen KNN. Now the other part that we want to see is decision trees. Now, can decision trees be used for regression? Yes, they can be used for regression also. Okay. Now let's get into decision trees. The first and foremost important point is it's a human like decision making process. Okay. So why human like decision process? We take decisions step by step. Okay. Now let's say I have a data frame wherein you have age, income, okay. Then you have, let's say, work X in years, and then you want to predict the price range of the house that you're going to buy. Okay. Now, let's say price range is okay. Now, let's say someone has already given you the data in terms of high, medium, and low. Okay. Okay. Any problem? I think I just saw a chat box. What happened? Okay. So basically, you are trying to predict whether the price range of the the house that you are going to buy will it be high. Let's say the high is greater than $200,000. Okay, less than 200K, greater than 150K. I don't know what are the basic prices in US. I'm just taking an example, and then less than 150K dollars is low. Now, when I build a decision tree on this, let's say my tree says if my age is greater than 40, okay, one way is the yes and the other way is the no. Now, there are two things in this. Who told you that age has to be first? Why not income? Why not work X? Okay. First question is this. The other question is why 40? Why not 50 or why not 60? Okay. So there are two things that we need to be clear here. Answer to the first question and answer to the second question is the same. Now, when we were doing the regression, what we were doing is regression objective function. What was it? Can people write down the answer uh, in the chat box? What was the regression objective function? Guys, can you write down the answer? Minimize the RMAC. Remember this. This is very important. Root mean square error. This is the objective function in linear regression, and this is the objective function that you have to use for all regression problems. For all regression problems, root mean square error is the objective function that you have to use. Okay, keep this very clear. Don't get confused because this is very important. I explained you yesterday also. Root mean square error is the objective function that you need to reduce for a regression problem. Okay, what was root mean square error? Sigma of y actual minus y predicted whole square, I equal to 1 to all the data points. Does everyone understand this function? Give me a yes or no. Or you need me to explain this a little bit more. Okay. Okay, so this is the regression. Any regression problem means any time when you are trying to predict, when you are predicting a continuous variable, this is the function that you have to keep in mind every time. No go around on this. Okay. Now let's first understand this. So let's say I said initially that age is greater than 40, then yes, then no. Let's build the decision tree first, then we'll try to explain further. So if your age is greater than 40, then I check. Then I check. There is another decision that I need to take. What were the features that we used? Income. Okay. So income greater than let's say $100,000. Yes. Then he's going to buy a high high priced item. Okay, high priced house. If it is no, then he is going to buy, let's say, a medium. If this will be low. Okay. Now another question that arises is, why didn't we check workx? Okay, why did I just say I stop here? I could have also had a kind of a decision tree like age a greater than 40, yes, no, and income greater than $100,000, yes, no, and then again I check workx greater than 10, yes, no, and then I finally predict. Okay, this is high, this is medium. Let's see. Now you see these two decision trees are built on the same data, but they have completely different meanings. Okay, so how do we how does the decision tree understand which decision tree is the best? So there's something called the entropy. Entropy is the loss function for a classification problem. Or you can also have something called Gini index. Okay. Now, what is Gini index? What is loss function? Gini index is basically sigma k equal to k to, or capital K, pmk into 1 minus pmk. Don't jump the gun here. I'll make you understand here. Okay. So this function you have to reduce. Now, what is this function? Let's go back to the decision tree that we were seeing. Okay. Now, can anyone tell me? Okay. Now, I'll draw another decision tree on the right. Can anyone tell me which is a better decision tree here? Just a guess. I mean, I am not looking for the right answers here. Can anyone just tell me which decision tree is better, whether a cut on age greater than 60 and left one? Sunil, that's perfectly correct. Left one. Why do you say so? Can you give me an explanation, one liner explanation? No, that is what. So Sunil says that the guy has more time to work. That is your understanding. I'm talking about how the data has, figured out. Why did age is greater than 40 is better than age greater than 60? Okay, I'll answer the question. So if you see here, exactly, Vasan, exactly, that's perfect. The left one has more distinct decision and that can be made easily. For example, here on this side, you see high is zero point 0.8, medium is zero point 0.1, low is zero point 0.1. So there is no confusion at all. 80% of my people are preferring high, 0.1% is medium, 0.1% is low. So I have a clear winner here. But if I say the right one, I mean, even on the right side, I see there's a clear winner here. Okay, so medium is 0.7, high is 0.2, low is 0.1. But if I see the right one, none of the decisions are very clear. Here the decision tree is confused. It is giving 50-50 probability to both. Here also it is not very clear. It's just 60% and 40%. So my decision tree is not very confident, right? It says, I don't know, it probably can be 60 or 40. Okay, so on the left tree, you cannot, Vasant is asking, you cannot have a proper decision on the left tree. I don't want to have a proper decision on medium and low. I want to have whether it is high, medium, or low. On the left side, I see high is 0.8, I give high. On the right side, I give medium as 0.7, I give medium. Okay, I don't need to understand which is, how the other things are, how the other categories are having the probabilities. I just need to find the maximum. And the question is, which maximum, which is more confidently higher than the others. Just hold on for 1 minute. Just hold on for 1 minute. Yeah, sorry for the disturbance. So on the left side, I just need to assign whether it is high or low, or high or medium or low. I don't need not. So for on the right, for example, on the right side, you're correct. On the right side, if I see this one, right, I see high as 0.6, medium as 0.4, low is 0. If I take the maximum from it I'll assign high here. And if I take the maximum of it, I cannot assign. I am confused. But your high is not very high compared to others, right? Get my point? It is not very distinct. Here high is, it is pretty confident that 80% is high, but here only 60% is high. Okay, so now for each of the classes here, your k is for each of the classes, and the m is the number of divisions. Okay, so how many divisions you have? We have 2. Okay, so in 2 means for the left one you have 2 I mean 2, let's say, okay, one thing I forgot to tell you, in decision trees this is called node, and these are called branches. Okay, I mean, whatever you understand, right? A node, and the last ones, when the decision is over, it is called terminal nodes. Okay, so for example, for my decision tree on the right, on the left, I have exhausted all my decisions, and I've arrived at a decision on my terminal nodes, and each of the terminal nodes now, let me get a new color. Okay, so on this side, what do we see? If I calculate this, high is zero point 0.8 into 1 minus 0.8 plus 0.1 into 0.9 plus 0.1 into 0.9. This is for the left division. For this, it is 0.2 into 0.8 plus 0.7 into 0.3 plus 0.1 into 0.9. How I get this? P into 1 minus P. P into 1 minus P. So P into 1 minus P. P into 1 minus P, and I add them. So you get a particular value. Similarly, you do this and you get a particular value. What do you think? Which will be higher? The right one or the left one? It's a mathematical question. You may be wrong here, but can you give me one answer? Which do you think will be higher? Left one will be higher. Okay. So the thing is, A into 1 minus A is the maximum at A equal to 0.5. Okay. So here the probabilities are closer to 0.5, whichever, because the larger number of probabilities are closer to 0.5. Okay, I understand this will be 0. Okay, but these will be very high. Okay, so because, so for example, let's see, let's calculate a sample. Zero point 0.2 into point is 0.16, right? And this is 0.21, this is 0.09. Okay, this is 0.09. However, zero point 0.5 into zero point 0.5 is 0.25. So 0.25, so it is always maximum when A equal to, I mean these are equal. Okay, so it is always highest at this point. So whenever, it means whenever you have the probability distributions uh, closer to 0.5, I mean closer to the middle, the sum will always be higher. You can check that after you in the class. You can check that after the class. Do the calculation itself yourself and calculate, and you'll see that the right one is higher. So what does this mean in terms of values? It means the decision tree has to minimize the Gini index, right? So whenever this Gini index, so for example, let's say I have a decision based on age and I get high as 1, rest all are 0. Here I get low as 1, rest all are 0. What will be the Gini index of this problem? Okay, same on both sides, Sharad, that's correct. But what will be the value? 0. Perfect, Sharad. Absolutely excellent. So it will be 0. Why it will be 0? I'll calculate. So I'll just rewrite the formula here. Okay. So now I'm calculating for the left hand side. So high for this one. Okay. 1 into 1 minus, sorry, plus same on the right side. So it means, and if you see intuitively, you'll see that this is a very good decision, right? If my age is greater than 40, I am 100% confident that my he'll buy a high priced flight. If my high priced house. If my age is less than 40, I'm 100% confident that he'll buy a low priced apartment. Okay. So now I'll just rewrite everything. I know what is my Gini index. I know what is my RMSE. Decision trees minimize Gini index. Regression problems minimize RMSE. Okay. Now, second point. By reducing RMSE, we obtained beta naught, beta 1, beta 2. By reducing Gini index, we obtained what? What did we obtain here? We obtained where we want to place our cut. For example, age greater than 40. Okay. So initially I told you that there were two problems, right? Did I state that? One was that how to figure out this should be 40, and the other one was how to figure out that age should come first. So your decision tree will do an internal calculation. Okay, it will see age, income, work X. Okay, then it will see age, what is the minimum value, what is the maximum value, what is the minimum value, what is the maximum value, what is the minimum value, what is the maximum value. In between this, it will try to find out which is the best cut. It will try to find out which is the best cut, and in this it will try to find out which is the best cut. How does it find out which is the best cut? The one which gives us the highest drop in Gini index. So the cut which gives us the highest drop in Gini, we have see here we have already said the Gini index should be reduced, right? So it perfectly makes sense that I will take the cuts where my Gini index is reduced or I obtain highest drop. So for example, initially, let's say initially there were let's say high was 0.4, medium was 0.2, and low was so this 3, sorry, 0.4. So I mean out of 100 data points, 40 were high, medium were 20, and low were 40. Okay, so this was the initial distribution. After you get a cut at age is greater than 40, so a high percentage, so let's say you had uh, 40 data points here because all the high came this side and all the low came this side. Okay, so I think just a sec, low. So this should have some value. uh, so you understand this, right? That total, if there are 100 points, on the right you will see some points, and on the on the right you will see some points, and on the left you will see some points. Total this should be 100, and since my high probability is 1, all the 40 points have come from high here, and accordingly you need to, I just gave this as an hypothetical example, but when you are calculating from the data you need to understand that how the distribution has would be. So I see that my initial Gini index was high. Now my Gini index is 0. So I have received a cut wherein I get a maximum drop of Gini index from some, let's say, 0.16, it has become to 0. So that's where I say that that cut which reduces the Gini index, gets me the highest drop in Gini index, is the cut that we have to take. Okay, and now I'll pause if there are any questions here. Do we have any questions? I'll open for. Okay, if there are no questions, then that's good. Sunil has told me there's no question. What about Vasant, Sharad? Okay, great, great.
Shubdeep,
Yeah, yeah, yeah.
Shubdeep, so in Gini index, whichever is, we should take whichever is maximum, or
Sorry, I didn't get you.
means you're saying that it's highest drop in the decision, right? We should take the decision where there is a highest drop.
Correct, 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 correct.
So in that means it should be minimum or it should be maximum. Like if you have age age 40 greater than age greater than 40.
Correct.
So if I have high as 0.5 and low as, means all like 0.5 and 0.3, 0.2,
Correct.
then they should select only highs.
So
High
okay, no.
0.
So one is this one is the threshold setting part where we are setting the threshold based on the Gini index, and what you are saying is the prediction part. So whatever, so every time it is not possible to get the highest drop in Gini index every time, right? It's not possible to.
Your screen got
Right. Yeah, I think
un-
it got unlocked, so that's why. Yeah.
okay.
Every time it is not possible to get the highest drop in Gini index. Okay, so there will be certain instances where your Gini index is kind of not the lowest. Just hold on, I think there's some echo. Just hold on. Okay, you guys can see me now, right? Can you guys see
Yeah,
me?
we are able to see. Yes. Yeah.
Okay, okay. Yeah, perfect. Yeah, so what you were saying?
Yeah, you answered that question.
Okay, okay. Right, right. Okay, then if that is the case, then we'll move on to some concept called bagging. Okay.
Shubdeep, I have one more question.
Yeah,
So
yeah.
why did you select only age into
Okay, okay. So I selected a particular age. Just I mean, particularly age, just to explain. So there, so here, as I told you, that according to the Gini index, your sequence will be selected and the thresholds will be selected. So, for example, age is selected. Then after that, okay, I think you have got into picture a good point. So, okay, now let's see. In decision trees, it is called a greedy approach. Okay. Uh, what do you mean by greedy approach? The greedy approach is basically that. So, for example, when I said that when I'm trying to, say that my age is greater than 40 and less than 40, I'm trying to see what will be the effect of this age in my Gini index. Okay. Then I see that, let's say my Gini index here drop is zero point 0.1. In case of income, let's say 100,000, my Gini index drop is 0.05. And your work-X, my there's a particular threshold, it's at 10, and my Gini index drop is 0.02. Which one will you select for your first decision? You'll select age. Which one will you select for your second decision? You'll select income. Which one will you select for your third decision? You'll select work-X. So basically, your decision tree will be age, yes, no. Then there will be income. Here also there will be income based on some threshold. There will be yes, no. There will be yes, no. And then there will be work-X. Here will also be, there will be work-X. Similarly, here will be work-X. And work-X will have a threshold of 10. So yes, no. So this, like, here you have all the terminal nodes, as we said, right? So these are all terminal nodes. So whenever you have a test data coming, so a new test data will check his age, then he'll check, it will flow from here, let's say it flows from here, then you'll check his income, let's say it flows from here, then he will check his work-X, then it flows from here, and then finally you get a prediction, let's say this is median. This is low, this is median, this is low. Just, I mean, just I'm giving hypothetical assignments. Don't understand that as you know. So I'm just giving arbit. So you get the predictions here. So whenever a new test data comes, it flows through this. Accordingly, it will test and flow. The flow will be checked, and accordingly, you'll get a particular prediction. Okay. Now, why did I say it is a greedy approach? Because I only checked what is my Gini index dropped individually. What if I say that in case, for example, what is your net Gini index drop in this case? So this will be zero point 0.1 plus 0.05 plus zero point 0.2. That is, sorry, 0.02. Right? That is your net Gini index drop. Now, there can be a case wherein I say that if you take income, I mean, you take Gini index drop of 0.05, income as first, and then you take work X, and then you check the age, my net Gini index drops. So for example, here it is 0.17, right? 0.1, yeah, 0.17. But if you take this in this order, you may have a Gini index drop of 0.19. But since you were greedy, you didn't see the overall picture. You saw whichever is giving my greatest drop in the Gini index, I am dividing on the basis of that. So age is giving, okay, divide on age. Then income is giving, okay, divide on income. Then work X is giving, so I kind of sorted it, and I took the decisions. But but you may have some certain times that, so because see, the income decision that you will be taking is based on the divisions after the age. Maybe if you take your income decision first and then you take the work age and then you take the age, your net drop in Gini index is much higher than what it was here. But you didn't check this. So this is one of the disadvantages of decision trees. It does not see the holistic picture. It sees at every step. It sees which is giving me the highest drop in Gini index. It is not seeing the overall picture. My overall picture at the end might be even a better one, but decision tree cannot do that. Decision trees follows a greedy approach. Okay, so this is very important in terms of greedy approach. Okay, so Vasant, is this clear now? I think what you were looking for, I explained something different from that. But is your doubt clear during the process? Okay, perfect. Okay, let's take a break for about 4 minutes, and I'll be back. Okay. Okay, I'm back. So we are good till now. I'll just unmute you guys. Are we good till now? Everything clear?
Yes.
Okay.
Yeah, looks good to me.
Okay. So just let's go through the slide once. What we have mentioned here. Okay, so your first node basically is called a root node. Okay, so all are nodes, right? And the last one are called terminal nodes, but specifically the first one is called a root node. These are inner nodes because we have not yet reached our decisions. We are still in the process, and the last one where your decision has terminated, they are called the leaf nodes. Okay. Okay, so a tree is made up of row nodes. The top node is in a tree. You can also call this one as a root node. I already told you. Child, a node directly connected to another node when moving away from the root. So this is the child. This is the child of this node. Correct. So I mean, you get the sense, right? Parent, the converse notion of a child. I mean, if this is the child, this is the parent, right? So you get that. And leaf is a node with no children. Okay. So this particular guy doesn't have any children under it, so it is called a leaf. Okay. So I think we have already seen these examples. No need to go in depth of that. Okay. So can anyone tell me? Okay. I'll not ask this question here. So if you try to see, yeah, if you try to think that what we have been telling each other, that what we try to overfit, don't if you think very in a detailed way, don't you think that decision tree is kind of trying to overfit? I mean, what is it doing? It is trying to take decisions, then going down and down and down, and then it's trying to come to a decision, and it is, let's say, I can always have a tree, okay, based on some decision wherein I only have one person or one data point in a node. For example, if I go here on the last leaf nodes, if I go to a leaf node, there can be a certain condition that I build so many decisions down the ground, and I reach a particular point where everything is one. For example, I only have one data point, and I know that whether it is a yes or no, or whether it is a high or medium. Okay, I go so low. I mean, I've overfitted the data. I have come to the point that I'm seeing just a single point, like we did in KNN, right? If I see just a single point, I am overfitting. Decision trees can also, go, very deep down and try to overfit. Okay. So as a user, I need to control that. Okay. I don't want overfitting, right? We have already discussed this. Overfitting is bad. So I need to control my overfitting. So what does overfitting in decision tree, how can it be controlled? So decision tree is a recursive algorithm and it will keep splitting the data until each node contains pure set. Pure sets means, so for example, what is a pure set is wherein your Gini index is 0, or you have a particular uh, class in the high in having one probability equal to 1 and the rest as 0, or I mean it's a pure set. Okay, it doesn't have any adulteration, it doesn't have a mixed probabilities, it just has a single probability. Okay, so that is a pure set. So decision tree can go on since my since my aim was to get the minimum Gini index, I can always go to a Gini index of 0. Okay, that is something that we don't want to have it. Okay, just a second. Okay, so we get this. Now this means that decision tree will always classify the training data perfectly with the accuracy of 1. So as I told you, so if I try to fit the whole data, I'll go to a certain point where my accuracy is equal to 1. Training accuracy, mind that. Okay, training accuracy, not the testing accuracy. And this doesn't work on new data, as the tree has learned from the noise from the training set, and it's not general enough. Okay, so if you have tried your best to fit in the tree, uh, you have overfitted it, and then you have gone with a training accuracy of 1, you you get a new test and you will completely fail. It's kind of draw the analogy from what we did in regression. Okay, I'll just open my iPad and draw uh, the analogy so that it's easy to understand. Okay, you guys can see. Okay, perfect. So in a regression problem, I told you that if I have my data points like this and I try to draw a graph like this is overfitting, right? We remember this. Decision tree, if I have nodes like this, so these term same here. So these terminal nodes will overfit. Okay. So in linear regression, what I told, we kind of use a regularization, and have kind of something which is less variance and high bias. The same thing we will try to do if this is high variance, then I will try to control the depth of the tree. Okay, so it means, what is my regularization here? I will say I don't want, so here my regularization was, what was it? It was sigma of beta j equal to 1 to p. These are the coefficients of your linear regression. So this should be less than some, let's say, s threshold. Here your it's more intuitive to understand. So if your variance is increasing here, this side is your bias, high bias. So you're kind of wanting to achieve a midpoint, correct? And so what do I need to control? I need to control the depth. Okay. So so depth is controlled by the number of terminal nodes. So 1, 2, 3, 4, 5, 6, 7, and here also we have. So let's say my terminal nodes at my most overfitted model, you have 12 terminal nodes. Okay, I want to keep this at a cap. I want to cap it. I want to say that my terminal nodes should be less than 7. Okay, so that's how you control the depth of the tree. Okay, okay, now let's get back to my screen. Okay, so size of a tree, the number of nodes. So if I increase, my accuracy will be 1. But what is this accuracy? This is the training accuracy. And this is my testing accuracy. So at one point of time, my training will keep on increasing, but my test will reduce. We learned this when we were learning overfitting and underfitting. Okay, so I think this is very clear. So pruning is a technique in machine learning that reduces the size of decision trees. Now pruning reduces the complexity of the tree classifier. Pruning is basically the cutting the tree from the nodes. Okay, but there can be two types of pruning. There can be pre-pruning and then there can be post-pruning. What is pre-pruning? Pre-pruning means beforehand, whenever I am building a tree, let's say first cut I get 2 nodes, second cut I get 4 nodes, third cut I get 8 nodes, and my threshold is, let's say, 7. So I don't take the third cut. Okay, so I do not go into the third cut. So my tree is only restricted to 2 cuts, first and second. Now what is post pruning? Post pruning is you build the whole tree, let it go till the last point, and then cut from below. Okay, so it has gone to the last node. Now from below you're trying to go up and see which particular let's say decisions don't make sense. And why we are doing this? Because we are seeing that, you know, your decisions should be more holistic. I should not stop the tree from growing before I've seen everything. Okay, so I should not restrict the tree to second cut when I have not even seen the 10th cut. Let it go to the 10th cut and then I'll cut from the below and see which is the most optimum case. Okay, now in the most optimum case, what you'll see, you already ask the tree to go to the lowest possible point. Okay, what you see is when you come back to the top, to your root node, you see how each of the cuts had affected the Gini index. So let's say from 9th to 10th cut, the Gini index was not that great a drop. You come up to the 8th cut. You say, I don't want my tree to do the 9th cut. Then you see what was the difference between the Gini index between 7th and 8th. Okay. And then you see if it is good, then I'll keep it. If it is not very effective, then I'll also not keep the 8th cut. And so on. Okay, so you come back from the bottom and you start to ignore those cuts which don't, not ignore, you take out those cuts which don't make much sense. Okay, so that's how what pruning means. So let's understand what each of these means. What is the max depth? The max depth is the maximum depth of the tree. I've already told you. So what is the depth of the tree in case of 3 cuts? It is basically 3. So I don't want the tree to go beyond 3 cuts. Okay. Minimum samples leaf, it means the minimum number of samples required to be a leaf node. So can you get a correlation between this? Can you understand this? Max step is something which is controlling the number of cuts. What is the minimum sample sleeve doing? It is also controlling the number of cuts. How? So let's say when I keep on cutting, the number of data sets in a particular node keeps on decreasing, right? Okay. First I'll explain these through, and then I'll draw it on my iPad so that you guys understand better. So minimum sample sleeve is basically the minimum number of samples required to be a leaf node. While I go down, okay, I keep on decreasing the number of data sets in a particular node, okay, and since I keep on decreasing them, I can reach to a point where there is one data point. Okay, so I control that, and I say no, I don't want to go to that point. I just want to keep it till, let's say, 20, let's say 30, let's say 35, something like that. Okay, max leaf nodes is tree cannot exceed the specified number of leaf nodes. So everything in essence is controlling the depth, the number of cuts. Do you guys get this, or should I, you know, draw it and show it to you? Do you guys understand this? Okay. So we learned that there are three things. One is the max. One is the max depth. One is the minimum sample. Yeah, I'm sharing the other screen, the iPad one. Okay. Now, so your tree basically is like this. Okay. So max depth is controlling this. Now, as I told you, when you keep on going down, the number of data points in each node can go up to 1. I mean, what I just told, I'm trying to overfit so much that each of this node is pure. And when it can be absolutely pure, when you have just high one data point, and that is high, or let's say if it is medium, there's no probability. It's a sure shot event. Okay, so you're going so down that you are trying to overfit. So what do you say? I want to control this parameter. I don't want my tree to go to such a point where it just sees one data point in a leaf node. Maybe it can be, let's say if it was 20 here, it will be restricted to 20. It will not go down lesser than 20. Okay, and maximum number of leaf nodes is in how many number of leaf nodes you have. These are leaf nodes, right? How many number of leaf nodes you have. If I rest, if say for example at this depth there are 40 nodes, I restrict them to, let's say, 10, and I end up here. So every parameter out of these three is essentially controlling the depth. Now, do you get this? Okay, awesome. Okay, then let's move on. Now, I've told you guys that decision trees can be used for all the thing that I've told you right now is for classification: high, medium, low, high, medium, low. What if you actually had the let's say you had the actual prices, $1,20,000, or let's say 10 $1 million, whatever. What if you have the incomes, right? So in income, if you have a continuous variable, then what you will be reducing? The RMC. Okay. Now, basically, what you will do, you're going to go down in a tree, and as you go down, there will you will be reducing the number of data points in a node, and these nodes will have an average price. Okay. Now, let's just understand this first, and then I'll draw it and show you so that you understand it better. So before that, okay, let me draw it only. Just let's go through the point here. Easy to visualize and understand the model. That's it, because you're seeing the tree in your you're seeing the tree. That's why it's easier to comprehend why the decisions have been made, and it is more easy to visualize. Least pre-processing of the data needed, so it is very versatile. When we code it, we'll come to know why it is very versatile, and helps identify irrelevant features. Now, this is something that I think Sunil had. Sunil and me had a discussion, right, when we were doing linear regression, and you were asking that how, or was it Sunil or I don't remember who asked me, but there was at this point you had to. They were asking that how do you check out the features which are relevant and not relevant. So decision trees are one of the methods or one of the algorithms which help us to gives the user the information that these are the features which are relevant and these are not. And this comes very handy when you fit a model. Okay. Why it can tell which feature is important and which feature is not, because it is taking decisions on single features, and based on the Gini index it can say which feature is important or not. They are very fast. Disadvantage is that kind of tries to overfit. Okay, this is very good. The second point, I'll draw that on my iPad and show you. The divisions are only perpendicular to the axis. It is not curved. Okay, an algorithm is greedy. I've already told you this. You may not find the best possible tree. Okay, so I need to make you understand two things, right? The second point and the first point. Okay, so let's go on to the iPad. So in decision tree classification problem and decision tree regression, right? Two things we want to see. In classification, what we had, I'll again reiterate this, right? What we have is Gini index minimize. In regression, what we have is RMSE minimize. Okay. So you have your Gini index minimize and RMSE minimize on either of side. Here you have probability distributions. Here you have, what do you have here? So for example, I'll go to the same, let me take another pen. Suppose you are now trying to predict the price in a continuous variable. So earlier you had high, medium, low. Now you have actual numbers, 100,000, 120,000, and so on. Okay. So now, for example, you age greater than 40, yes and no. So for example, initially you have 100 data points. Now here you have 60, and here you have 40. Okay. These are the number of data points. Okay. Not now these 60 data points will have something called these 60 data points will have a price associated with it. So I take the average here as a prediction. These 40 data points will have an average. I take this average as the prediction. So whenever a new data point comes in, test data point, I check his age, and then I accordingly, let's say the new is 45, so it will flow from here, and I predict this, whatever was the average of those 60 data points. Similarly, if it is 35, I predict this. So I think this is very clear. The other thing that I wanted to explain you is, if you see this on a graph, for example, you want to see income and you want to see age, and let's say your data points are like this. Whenever you're doing a split, you're doing it up as a perpendicular, or age, okay, so you're doing a cut which is perpendicular, and then you again cut on income, which is a perpendicular cut. Age, this is 40, so whatever is greater than 40, whatever is less than 40. Income, let's say you cut on 100,000, so whatever is above 100,000, whatever is, so you're doing perpendicular cuts. What if your data is kind of circular? What then? If you do this cut and this cut, does it make any sense here? So decision trees are good for cuts which are separable linearly. So if your data is something like this, okay, so it can be linearly separable. Or then, but if you data is completely circular, or let's say it's, if in a 3 dimension you say it's a spherical, then decision trees will fail, because decision trees will always have cuts which are perpendicular to the axis. Okay. Okay, so I think this is pretty much clear. Now let's move on to a new topic called bagging. What is bagging? Bagging is basically a process in which you're basically taking random samples from the data with replacement and fitting the model individually on each of the sets, and then taking an average. Now let's see what I mean here. A process in which random samples from the data, so let's say you have 1 to 100 data points, you take any 40 data point, you fit a tree. This is tree 1. You take next any 40, next any 40, okay, random. This is random, okay. Random samples with replacement. With replacement means you take out, you fit a tree, and then you put it back in your data, right? So like this, you can fit 10 trees or 20 trees or 30 trees, whatever number you can fit, right? And then if it's a regression, take an average. If it's a classification, take the voting. Okay, so basically your model is something like this is the number of bags you want to take. Okay, so this can be 10, 20, 30, can be anything, right? And based on that, those many number of trees will be formed. So you this actually contains, each of these fx is a tree. So you take an ensemble is for example an average of whatever those 10 trees are saying. For example, let's say I have tree 1 on my first set of data, tree 2 on my first set of data, tree 3 on my third set of data, sorry, this is second set of data. So like this you have, this will have an output, this will have an output, this will have an output. Okay, like this there will be 10 outputs if you have 10 trees. What you want to do, suppose you want to predict the price. Okay, so feed in your test data in this tree, in this one, the same test data, and then there will be outputs here, 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 and then you take an average. Okay, so basically taking an average of 10 trees. How does it help? It is, remember always, bagging enables you to see different parts of the data without any biasness to any part. So tree 1 has seen a certain part of the data, tree 2 has seen a certain part of the data, T3 has seen certain part of the data. Since I'm taking randomly, there can be cases where they are same, I mean somewhat is similar, but they will not be fitting on the same data. So everyone is seeing some parts of the data. It's like you have, like the example I gave you yesterday. You have some problem, you ask your subordinates to go take this file and come up with insights. So your 10 subordinates will come up with 10 insights. As a manager, what you have to do is you take an ensemble or an average or a majority vote of all the insights that and get to the best solution. That's what your manager, that's what you should do as a manager, right? So everyone has their different biasness, everyone has their different opinion, and as a manager, you are taking an average of all those 10 people. Okay, so this is what you need to do here. Okay, so I think this is pretty much clear. Okay, now I will continue with this and state another concept called random forest. Now random forest is one of the, big concepts and one of the best concepts which, you as a machine learning data scientist, or as a data scientist, your first trial in a model fitting is through random forest. Okay, so your first approach is towards random forest, and it is a very important tool. It it takes care of all the advantages of a decision tree, but foregoes all the disadvantages of a decision tree. How? Okay, now we told that my tree 1, or let's say whenever I am building a decision tree, it's kind of doing a greedy approach, right? We told this, right? It is doing a greedy approach. It is trying to overfit, and what else? It it doesn't. So greedy approach is basically it doesn't know that whether this tree is the optimum tree possible or not, right? It is doing. It is just saying quick wins. It is saying whether this decision will go to the minimum Gini index. Perfect. Let's go. Yeah, doesn't work on circular data also. That's correct, Sharon. So let us write that. But I didn't write that because neither will random forest be able to work on that. But still, I think it's a good point that you brought. Doesn't work on circular data. So this is one of the major problems of your decision tree. So what does random forest do? Random forest is very clever. What it does is takes a decision tree, forms 500 trees. That's how the forest comes. The forest is made of a large number of trees. This is an example. It can be 500, it can be 1000, it can be 1500, it can be any number. Not 15,000, does not go so much. So anything between 200 to, let's say, 3000 is a feasible number. Okay. It employs the concept of bagging, and then the last, but the most important concept is random selection of predictors. Now this is the most important part of random forest. So we know decision tree, it fits 500 trees or large number of trees. It employs the concept of bagging, what we saw here. All the trees, like these 500 trees, are being fit on different data, different random selections of the data. And the most important part, it fits on random selection of predictors. For example, if there are 10 predictors or features, let's say, it doesn't take all the predictions into all the trees. For example, tree 1, T3, like this, T500. Vasant, okay, I'll come to that. Why do we have, Vasant is asking, why do we have 200 plus trees in our data set? I'll come to that. That's a good question. So I'll come to that. Let me finish with this, and I think you'll get the answer here. So it is fitting on D1, it is fitting in D2. These all D1, D2 are the part of the same data, but there are random selections. So this is a concept of bagging, what we saw. But even in the D1, I am taking random selection of the features. So for example, 10 predictors, I take, let's say, any 4 from them. Even in T2, it is taking any 4 of them. May not be the same. Again, I'm saying random selection. It is not taking the first 4 or top 4 or 5-4. I mean, last 4. It's not taking like that. It is taking random selection of features and building the tree on it. So T1 will be based on D1, which is a random selection of the data as well as the random selection of features. Similarly, D2 will be a random selection of data as well as random selection of features. So for example, let's say you have 100 data points, you have 10 predictors. Okay, let's say you have gender, you have occupation, you have work X, something like that. So in the first chance, it may take these 4, or it will take these 4, or it will take these 4. Okay, so it's like this. It takes random selections, okay, and fits the trees, and then it does the same thing as the bagging. It takes an average or a majority vote of whatever these trees have told. Okay, so now let's see if a test data comes. This is your new test data. It goes here, it gets an output. It goes here, it gets an output. It goes here, it gets an output. So it goes here, gets an output, takes an average and gives the value. Okay. Now coming to your question, Vasant, why do we need 500 trees? No one is saying that you need 500 or 200 plus trees. You can take any number of trees. But what we are trying to do here is we are trying to increase the randomness in the selection. And more randomness in the selection, the more is the probability of you landing into the best solution. So since we told that decision trees have a greedy approach, and this one, since decision trees have a greedy approach and you never know that your decision tree that has been fit is the best one, you're trying to see random selection of predictors. So for example, when you're taking age, you're not taking work. Let's say you're taking just age and occupation. Or let's say what we had here. What was the other feature we had? Age and income, right? Age, income, and work X. Okay. Age, income, and work X, right? So let's say first you take age and income, then you take age and work X, then you take income and work X, and if you take these different subsets, think like that. If you take different subsets, the probability of that the problem that you always take age first and then income and then work X reduces, right? Because at this point of time you're just seeing income and work X. The next point of time you're just seeing work X and age. The next point of time you're just seeing work X and age and income. So like this, there will be three combinations possible, 3C2. So so more the number of features. So the what you call the thumb rule is to have in a particular selection for a particular tree. So the thumb rule is number of predictors in a selection should be equal to the root of number of features. So at any point of time a T1, so let's say there are total 16 features in the data. T1 will take any 4, T2 will take any 4, T3 will take any 4. So this, using this, no tree will be biased of using a particular sequence. Every tree is seeing different sets of features, and every tree will have different set of understanding. So for example, if you go to your subordinate problem, right? So if you give everyone different set of data and different set of data to play with, people will come up with better insights, right? You give, let's say you give X guy, you just give him, you just see the top 100 rows and you just work on, you're basically kind of doing a divide and conquer. You're asking him, don't look at the whole data, don't get confused so much. What you do, since you are best at this, do this. You give the Y guy, since you are better at this, you do this. You give the Z guy, since you are better at this, you do this part. And then each of this, they come to you and say, see, we have got this from our part, and as a manager now, you'll take an majority vote or you take an average out of all these decisions. That's how random forest works. Okay, so random forest, the name itself, concentrate on the name. The name itself states random. Random means I want to create more randomness in the system so that I don't get biased. Forest means I need to do this by constructing a large number of trees. So using bagging and using random selection of features. Okay, so is this clear now? I think we have gone a lot of depth in random forest. That's great. That's great. I think everyone is clear with this. So let's take a 5-minute break. I'm really thirsty. Let me take some water. Okay, I'll be back in 5 minutes. Okay, I'm back. So any doubts? Amazing. Okay, so I think we are good here. Let's go ahead. So I think you can do this as a homework. So I'll just show you the code for decision trees. I think it's a very simple code. So from sklearn import tree, est is equal to est is a variable you are storing, and est.fit. Okay. So you see, criterion is a Gini index. Max depth I have not specified anything. Okay. So if you want to do, you can easily write here depth is equal to 4 or anything. So minimum sample, minimum weight fraction, don't go by this. Max depth and minimum sample sleeve is good enough. Okay, or minimum sample split. So minimum sample split is how many samples you require to have in your node so that you can carry out on the next split. Okay, so I think these are the, so what you can do is for your homework, kind of try to replicate this code for different max depth. Okay, so kind of replicate this code for different max depth and see how the scores, vary. Then what you do, you try to replicate the code same for different minimum sample split and see how the scores vary. You'll see how your overfit and underfit will vary. Do the same thing for the random forest. So random forest is also same. Just you can take max. Yeah, see here max features. Everything else is same. What you need to do here is max depth 1 and the number of estimators. So this is the number of trees. Okay. So if this is right now 10, 10 I just put a random number. You can put anything 200, 300. So write down this as a homework. Max features is auto. It's max features is like what I said, how many features you are taking as a random selection from the number of features. Okay, and start from 200 n estimators and go to let's say 1000 with steps of 100. So 200, 300, 400, 500, and try to replicate the same code for each of those and see how what happens. So this is your homework, and if you guys can do that, that's amazing. And if you have any doubts on that, we'll come back to it next week. Okay. So are we pretty good on bagging random forest and decision trees? Then I'll introduce another concept now. Everyone okay? Okay. So people are not comfortable with the code as I said. So I'll send you the code. Okay. I'll send you this notebook. What you have to do is you have to replicate the same thing. The cross validation. This is the cross validation. And for different, for example, you had neighbors here. Neighbors was the hyperparameter here. The hyperparameter. Okay. Yes, Sunil, I'm just coming to your question. Just wait for 1 minute. So here your hyperparameter is what I said. Here you keep max depth as your hyperparameter. So start your max depth from 2 and go up to 10 and see how your cross-validation scores change. Similarly, for random forest, change the number of estimators from 100 to 1000 with steps of 100 and see how your cross-validation scores. Let's go off. Cross validation. Try to replicate this. try to replicate this for random forest and try to replicate this for decision trees. Don't worry if it doesn't happen, no problem, but just try, okay, so that it becomes clear. Because if you don't code it yourself, it is going to be very difficult to understand. So I can do my best to explain you the theory, but the coding part, I can show you the syntax, but at the end you have to code. Otherwise, it will not help. So just try this part. And Sunil, your answer to your question, whether there is a data set for decision tree, any data set which is classification can be used for decision tree. Any data set which is regression, it can be used for a decision tree. So you can use Boston data set, use decision tree. In case of classifier, you just need to write regressor, or you can use the iris dataset that we saw last time yesterday. What we use for logistic regression, you can use the same dataset for decision tree classifier. Is that okay? Does that sound good? Okay, Vasan, are you good with the code? I'll send you this notebook so you can have a look at it, and I just want you to replicate. These are the hyperparameters. I want to pick one. Pick. I want you to pick just one max depth and see for different max depth how it changes. Similarly, here I want to see for different number of estimators how your scores change. Okay, so you just need to, in place of neighbors, you just need to have that array, and you need to find out the scores for each of those arrays. Okay, so I think this you can do, no problem. So I'll move on to the last topic for today. I'll go to my iPad. Okay, can you guys see my screen? Okay. We come to a topic called boosting. So till now what we have seen, we were having a parallel approach. T1 was working independently, T2 was working independently, T3 was working independently, T4 was only like this. 500 trees were working independently on different data sets and different set of predictors. Correct? Now, boosting is little difficult, different. Let's take uh, this color. Boosting, what it says is T1, you see D1, okay? You try your best, whatever you wanna try your best on D1. Then give me whatever you could not fit. T2 will get this is the whole D1, okay? This is a whole data set, not D1. Sorry. T2 will get whatever T1 failed to fit. So let's say T1 was classifying, T1 was doing a classification problem on D, and it was classifying yes or no. There were 100 data points. 95 of them was predicted correct. 5 of them were wrong. I mean, the actual was yes or no, and I just predicted the reverse. I predicted no for yes and yes for no. So 5 of them were wrong. So T2 will say, make sure when you pass me the data. Okay, sorry, one thing I told you wrong. This is D1 only, okay? So this is a sample, random sample, not the complete data set, okay? So this is D1. So T2 will say, I will take D2, but make sure that the part which you failed, T1 failed to fit for D1, make sure this part comes to me. I already have D2, that is okay, but I want to make sure that these 5, so these 5 should come to me so that I can do a better job, at least to fit 5. So T2 does a good job. T2 says, okay, I'll fit these 5, but in this process, it missed a different number of 3. I mean, different data set. So, so for example, he also got 100. So he did a perfect job on these 5, but since he was too much concentrating on this, he forgot to fit these a different set of data sets. Three items it did not fit. So your T3 will say, don't worry, I will fit this 3. I already have something on my plate, but I'll do my best to fit this 3. So like this, the series will go on. So this is called a series learning. Each of the next 3 tries to fit what the previous one could not. So each of the next 3 tries to fit what the previous one could not do. Okay. So every time it is boosting the error that was left by the previous. Okay. So this is what is boosting. Rest everything remains same. You fit a large number of trees. This is also of the order of 200 plus to 3000. Okay. And you see the different number of data sets. I mean different uh, sets of data like D1, D2. Yes, but you don't see different predictors. I mean, you can do that. You can see different number of predictors, but usually it doesn't happen. You don't see different number of predictors. You see different number of data sets. Okay. So with this, we can conclude today's theory. Okay, and Uh, okay, one more thing I want to tell you. This is done. So Vasan, you say, asking you're trying to fit all the data, as in you're fitting subsets of data. So for example, 100 rows are there. You're taking 20, let's say 40 here. You're taking another 40 here, but you're making sure these 5 come. So you're basically taking 35 from here, but make sure that these 5 come to T2. Then again, 3 have been left. So it takes another 37, a different set of 37, but it makes sure that 3 comes. Okay, like this. So you try to fit all the data. I mean, it's again the same thing as bagging, right? With different random sets of D1, D2, D3. Okay. Okay. So I think today was good in terms of pace. We have completed a lot of things. So what I will do is you will code the random forest and a decision tree with the different hyperparameters. Okay, as I told you, and then I will show you one of the boosting algorithms, and we will see how this increases the accuracy much better than all the previous algorithms we have seen. Next class we will do naive Bayes. So just let me give a brief picture of naive Bayes. What is a naive Bayes algorithm? So there's something called Bayesian theorem in probability. Conditional probability. Let me write the this thing first. Okay, so naive Bayes works on this probability of y given x. So probability of y equal to, let's say, high, the same example what we saw, given x equal to, let's say, x is age, equal to greater than 40, is equal to probability of age greater than 40 given y equal to high into probability of high. What does this mean is, this is basically what you could say is something like it's a Bayes theorem simplification. So everything in statistics is based on probability. Okay, so what we are trying to say here is the probability of your price income, or sorry, the probability of a person buying a house of high price given that his age is greater than 40 is equal to what is the probability of a person having age greater than 40 given he has bought a high priced house into the probability of a high priced house. Forget this. Forget this. Don't concentrate on that. Understand this. Okay, let me prepare a data set. Yeah, forget income. Forget. It has frozen. Suppose you have a data set of just these points. Okay. Now this is called the likelihood. So what is the likelihood of a person whose age is greater than 40, given he has bought a house of high price? So if you take the high price houses, how many are those? High prices how houses are 45, 47, right? So what is the probability that a person's age is 40, given he has bought a high price house is 1, right? All the people who have a high price house, he in this case, are aged greater than 40. So this is 1. What is the probability of high in your data set? So high is 2 divided by 1, 2, 3, 4, 5. Right? So basically 1 into 2 by 5, that is zero point 0.4, is the probability. So whenever you have a test data set coming in and his age is greater than 40, so the probability of him buying a high priced house is 0.4. So this is naive base. We'll continue in detail in the next class. Meanwhile, just read about these two things that I write. One is a conditional probabilities and one is the Bayes theorem. Read about these two things when we meet in the next class. And so today we will conclude, and let me get to my yeah. So today we'll conclude here. If you guys have any questions, we can have a 5-minute question answer session. I'll unmute you guys. Yeah. So forum is open for questions. Any questions you have? So does this help, drawing simultaneously and explaining? Does this help?
Yeah, absolutely. That was great. But I think so if that drawing can come over our slides, as previously we were writing over the slides, that will be great.
Okay.
Because this is as like context switching. If you're going through the slides, now you're moving there. But earlier, I think so. And writing, that was stuff. That was the issue.
Okay.
As I
So
think so.
what I'll do is I'll put the slides in my iPad so that with the slides we can see on the iPad itself, and for the code we will come to my desk laptop. Okay. So when we do a coding, because coding we usually do it at the last, so coding
Yeah.
we keep it in the laptop, and the slides and the writing will do that in the iPad. That's okay, right?
Okay. So one more question. You means that, but my question on the question said, which are the predictors which we can remove? So for that, first, do we need to use this decision tree to remove a few of them, and then later on
Okay, so
they can
decision,
use in
we'll see that in the next class. We'll see what is Baruta plot. I will show you on the Boston dataset how you can apply Baruta plot and get find out the relevant features. I'll show you that next class.
okay, and that Baruta plot we have to do manually or
No.
automatically there is some algo. Okay,
I'll tell you. I'll tell you. Don't worry. I'll tell you next class. I'll show you how you can apply Baruta plot and get back and get the answer.
okay. So what are the means? What are we are going to cover in next week
Next
other
class,
than this naive bias?
next week will be naive bias. Then there will be support vector machine. Then there will be unsupervised learning, clustering, and then probably we can take up gradient boosting. Um, uh, yeah. So I think to next by next two sessions, we will close all the models, and then the next session will be a project work, wherein we will try to apply all the models and see which is the best.
Okay, and then last means third one will be our project work which we have to do by ourselves.
No, project work I will do with you guys, so I will show you the
I
code.
think okay.
Yeah.
Okay, and what is this K mean? Means that is the median. Sorry, I mean
Sorry.
root square mean value we are taking. There is one more algo I was going through yesterday. K means
Okay.
model.
Yeah, we'll go to that. K-means clustering. That is an unsupervised learning model. We will go to that when we do unsupervised learning. Don't worry. We'll see that.
Okay, that's great. Thanks, Sweet.
Okay, no problem. Thank you so much. Take care. Have a very happy.
Thank you.
Okay. Thank you so much, guys.
Happy week ahead. Thanks.
Thank you.